Now let's talk about some issues that occur when we're designing systems using interrupts. The first one we're going to talk about is cached memory. So the problem is when we have a situation where we are running some main code that manipulates a variable that is also being manipulated by an interrupt. So in this case, we've got two examples of code. I've got my main down here with a global variable called C that's being modified inside of main, and I've got an interrupt that also modifies C. So you can see that when the interrupt is called, we basically want this for loop to exit. We want to kill this for loop, right? So let's see what happens as we execute this. The first thing that happens is whenever we're manipulating C in main memory, the common pattern for this is for a copy of the variable C to be copied from main memory, from RAM, into a register, into a temporary register. And that's where we modify it. So here we're incrementing C, everything's fine, and then after we increment it, it gets copied back into main memory. We go through it again, we copy C, and in this case, we trigger an interrupt, right? So here we've got a copy of C, the current version of C in the temporary registers, and we've also, interrupts always operate on main memory, right? So that well, actually, it might use a register, you might use a temporary register, but it's not going to overwrite the one that's already in the temporary register. We're going to try to avoid that. So the change for the interrupt is reflected in main memory, but it's not reflected in the temporary register. So if we paused and handled this interrupt during the time when C is being updated, when we resume, we increment C in main memory, or sorry, in our temporary registers in the main function, and that 3 overwrites the variable C that's in main memory that we had updated with the interrupt, and now it's like the interrupt didn't happen, right? So the way we resolve this is using what's called the volatile keyword. And basically what this does is it directs the compiler to treat the C variable as changeable at any time, which basically it is if we're using it in an interrupt. And it prevents the compiler from using C as a in cache. So there's never a duplicate copy of C. We only end up with one copy of any volatile keywords, and we never have the situation where the main function changes it, the interrupt changes it, and the change is overwritten by the main function. It's only ever changed in main memory because we only ever access it directly in main memory. Now this slows things down a lot because the registers are much faster access. So every volatile keyword is now a RAM only variable, and that takes much longer to do, especially if we're doing a lot of little operations to it. So use the volatile keyword sparingly and only when it uses interrupts. The next issue we're going to talk about is race conditions. So here I've got a little program where I've got an interrupt that updates a variable called raw accelerometer, and I've got a decision in my main loop that uses the variable raw accelerometer. And basically the rule here is that in main I should never display raw accelerometer unless I should never display raw accelerometer if it's 0. So I should only display it if it's non-zero, right? But the problem is in this situation we do end up seeing some zeros, and the reason why is because in between this decision here sometimes we'll get, and the display function, sometimes we'll get a little interrupt trigger, and that changes the value of raw accelerometer, which might be 0, right? So the solution for this is to enforce what's called atomicity, and basically it means that we don't want certain sections of code to be divisible. We don't want it to be possible to interrupt between certain sections of code, and the way we enforce that is by using the enable IRQ and disable IRQ methods, and these are global enable and disable functions. So basically it disables all interrupt requests or it enables all interrupt requests, and this is how we prevent interrupts from occurring during certain blocks of code, enforcing atomicity of certain behaviors. And we might want this when we don't want something to change, or we have some critical behavior that's dependent on a variable, and if it changes halfway through a process, we don't want that to be affected. We want that process to complete entirely before it finishes. So let's review some of these danger zones. The first one is to avoid processor starvation, right? If you've got a lot of interrupts occurring, the main function won't be being serviced. If they're happening too often or too fast or they're taking too long, you want to make sure that interrupts are infrequent, that they're short, that they execute quickly, and they return back to main as quickly as possible. You also want to be aware of race conditions. This is the enforcement of atomicity that we just looked at. And if you have variables that are changing during processes that are executing, make sure to prevent that from happening if it's design critical. And finally, interrupts are equivalent to multi-threading in a kind of way. And basically, we make them thread safe by using the volatile keyword. So that's another set of tools in our toolbox for handling issues with interrupts.